Here we're going to look at an example of writing a combustion reaction and balancing the resulting equation. So we're starting with butane, C4H10. We know that we're going to have to add oxygen, and we're going to have two products, CO2 and H2O. So the first thing I'm going to do whenever I'm balancing any equation is tally up what I have, carbon, hydrogen, and oxygen. And I see that I have 4 carbons on the left, 10 hydrogens, and 2 oxygens. On the right, I have 1 carbon, 2 hydrogens, and 3 oxygen atoms. So that's going to be where I'm starting at. The first thing I'm going to look at is my carbon. I see I have 4 carbons on the left and only 1 on the right, so I'm going to put a 4 in front of the CO2. When I do that, that changes my number of carbons to 4, which is great because that balances that. And it also changes the number of oxygen, so now I have 9 oxygens because I have 8 here with the CO2. 4 times 2 plus 1 more is 9. Because I have oxygen in a couple of different places, I'm not going to worry about balancing that yet. I'm going to save that until the end. The next thing I'm going to look at is my water molecule because I'm going to add a coefficient there in order to balance my hydrogens. I have 10 hydrogens on the left, 2 on the right. So if I put a 5 there, that's going to give me 10 hydrogens on the right, but it's also going to change the number of oxygens. So now I have 8 plus 5, or 13 oxygens. So now my carbons and my hydrogens are balanced, but I see that I've got my oxygens unbalanced. And unlike the other example of a combustion reaction we looked at, we see that we don't have just an even number of oxygens. There's nothing I can clearly put in front of that O2 in order to get the equation to balance. So what I do is I pretend for just a moment, okay, that the oxygen is not a diatomic, that it's just O. And I say, well, what would I put in front of the oxygen in order to get that to balance if it in fact were just O all by itself, no subscript? Well, I can say that would be a 13 because that would give me my 13 oxygens on the left and I'd have the 13 on the right. Now, I can't just lose the subscript. So I see that it should be 13 oxygen atoms, but I've got to remember that I do in fact have that 2 there. So when I go back to put the 2 back in, what I simply do is make this 13 halves. So 13 halves times 2 is going to be equal to 13. So I get my 13 oxygens on the left and my 13 oxygens on the right. So now I do actually have a balanced equation. However, I don't want to leave that fraction in there because when we balance an equation, we always want the smallest set of whole number coefficients. But I can't just multiply this number by 2 because that would just change one thing. I need to multiply everything by 2. So I can actually go through and change my coefficients. I'm going to multiply everything by 2. So I have 2C4H10 plus 13O2 yields 8CO2 plus 10H2O. Now I can go back and check my calculation here, check my counting to make sure I still have a balanced equation. I have 8 carbons on the left, I have 8 carbons on the right. I have 20 hydrogens on the left, I have 20 hydrogens on the right. I have 26 oxygens on the left, and I have 8 times 2, that's 16, plus 10 there gives me 26 oxygens on the right. So I have a balanced chemical equation. And so this is just a little trick that you can use when you're dealing where you have an odd number of oxygens on the right side and you're trying to balance that on the left, where you know you're going to eventually have an even number because you've got O2 there. So we just pretend for a moment that the 2 isn't there, figure out what we should have, and then put that number over 2. Doesn't happen very often, but with some of our alkane compounds we do see this.